Netrasri and Nurul. Can you wait for 5 more minutes so that if anyone can join? I think we will start the class. Can you hear me?
Yes, sir.
Thank you. One second. Let me share the screen. So, can you able to see the screen, the PPT?
Yes, sir.
Okay, fine. So basically, this is the second week of the thermodynamics TA session. So in this class, I will go through the first 5 minutes of what we have discussed the last week and what we are going to discuss for the next following 1.5 hour. So before that, if you have any doubts, you can ask me regarding the class week 1. If you have no doubts, then I will continue with the class. Okay, I hope there are no doubts. So yeah, so we started with the what is system and what is surroundings, followed by we followed through the systems. Okay, what are the different types of systems we have? Basically, to talk about it, we have open system, closed and isolated. So then we have how can we describe the system? Say suppose like as we says that okay, we have this particular system and how to this was okay. What is the temperature of it and what is the pressure? What is the volume? What is the density and what are the different like how many number of moles it has? Uh, every other properties, and these all are microscopic properties because we are not focusing on any particular molecule and how the molecule is changing. And yeah, as with the title of our NPTEL class says, there are two types of thermodynamics. One is classical and statistical. So once if you have approached through macroscopic, it is nothing but a classical, and if you go through the microscopic, it will be a statistical. And you all know that what will be the like extensive intensive variables. You need to remember that extensive is the one which if you change the system size, it will change, and intensive are the one which remains the constant. So basically which say suppose if you take the ideal gas condition, which is PVT, where we will take the volume as a function of pressure and temperature, so that we can find out the thermodynamic state of the system. So I will explain you that in the later part of the today class. So once we have classical and statistical, then we have the thermodynamic laws. So as you all know that there are four different types of laws, starts from the 0 to 3. 0 deals with the temperature, and then first law deals with the energy, and second law deals with the entropy, and third law deals with the numerical values of the entropy. So as we all discussed that how the temperature and so as we already discussed that in thermodynamics, what do you mean by equilibrium is at any macroscopic level, if the system attains a state where it appears to be that there is no change in the system, then it is up to be called as equilibrium. It doesn't mean that equilibrium means if you keep, suppose if you have if you hold a cup of say suppose isolated mug of coffee, and if you kept it here for 1 hour and then later you will take it some other place, and after for some time it will attain certain temperature and pressure, that itself is called as equilibrium. It need not to be the same like from the initial to final. So regarding that, and there are two different types of systems. So initially we have discussed closed system, open system, and isolated types. Here what are the different types of system is what is the different types of liquids we have phases in the system. Say suppose if you have the, as a best example is coffee. If you take the coffee example, it will be like homogeneous, because all are in the liquid phase. There is no different solid or gaseous phase. If the phases all are in the same phase, it will be considered as a homogeneous phase. If you have more than one phase, it is called a heterogeneous phase. So these are the best example: coffee in thermos, mocktails, the dry natures. And further, if you go through it, heterogeneous are like if you have more than what you call two phases, like a glass of water and wind, mixture of water and oil, a boiling of water, where you can see the it's an open system, basically boiling water, where you can see the water and temperature, and we will talk about the much more of boiling water example. And we have the state variables and path variables. So basically path variables, what we will call is, say suppose if you are going from one place to another place, we don't care about how we went or anything. So basically we'll say that suppose if you are taking the flight from, just to give the one small example, you went from point A to point B, and you don't care how you went. It is called a state variable. So you are saying that, okay, I have taken the initial position and I have final position. I started at 9 o'clock and I reached by 12. So if I ask you like how much time it will take, you will say 3 hours, and you will not talk about that, okay, how much time it is taken at the point junction A or another junction to reach the B. So that is called as state variable. Once you are talking about the path variable is nothing but you will encounter all the basic things which will occur in the steps from going from A to B. That is called as path variables. So if I talk about, say suppose in the I think you have one assignment question also in the week 2, I think, which is called as state variables and path variables. So basically if you consider path variable means just have one assumption, just have one small how to say it, just have one small identification saying that, okay, if I say path variable, or if I say state variable only depends upon the initial state and final state, and the path variable depends upon the intermediate states from the going from the point A to point B. So you need to remember these two. And we have the two examples which I says that, okay, how can we go from point A to point B. And then so we have the zeroth law. So basically zeroth law says that the heat transfer from the between two bodies. Say suppose if I given the example that it says that the heat transfer from hot body to cold body. And what the use of this example was, say suppose if I have the how the temperature thermometer was identified was using these systems. So what here I'm saying was, say suppose you have the two different temperatures, say suppose at point A and point C, and you know that how can you say that, okay, using one thermometer scale you can say that, okay, using what will be the temperature differences between A and C. So this is the how the basic zeroth law is defined. So in old days there are many zeroth laws. So basically it starts from the Celsius, Fahrenheit and Kelvin. So yeah, how can you say that, okay, there is a variation in the temperature and how much variation it will happen. So initially they have taken the water boiling point and water the freezing point as two minimum and maximum temperatures. Based upon this they have played around it. So if you take that and in some cases they will take the, suppose if you take the steel, heating of steel, you can see that heating of steel will be in the full of in the red color, more of orangish red, and then once you cool it in the water you will see the change of the color. So that is also another way of form of checking the temperature changes. So basically in thermometer scale they are using the mercury. Along with the mercury they will see the rise, how much rise is taken, and they are saying that, okay, with the reference of water point, say Celsius do it with the reference of water, and Fahrenheit has done for the human body the warm temperatures. So you can say that yeah, once. So what does the ideal gas theorem says was, so we have the two different indistinct intense two different states like P and V, which is which are responsible for using the function of T. T is nothing but temperature, and we have the freezing point of water and boiling temperature, and we have seen the graph saying that if you take the linear interpolation of the graph extension, we got the minus 273 as the basic point. And then we have the Kelvin scale. If you see that there is a Kelvin scale with T of k with 1 second, I think I can move this. Yeah, T of k with the 273.15. So once, yeah, 1 second, 1 second, yeah, so yeah, this is correct. So yeah, once we have done with the Kelvin scale and we have taken the triple point is the water where so now as the Celsius taken the 0 degree and 100 degree Celsius, in the triple point we have taken the reference point as the where the water has reaches. So it is a 273.11 Kelvin and 611.73 Pascal. And then we went through the ideal gas law. Okay, how to obtain the ideal gas law and where we have got it. So we have taken any two parameters. You see, suppose as I said that we have taken the function as a volume as a function of two intensive variables, which is P and T. And then we got the equation, and further to extend that equation to the real gases, we got the van der Waals, the best one for the real gases. So, and here are the few examples I said. And
Excuse me, sir.
hello.
Excuse me, sir. Can you explain the relation for the real gas?
Okay, this one.
Yes. Yes, sir.
Say suppose we have PV equal to RT, right? So if you have PV equal to RT, just imagine that why we are doing this one was, so PV equal to RT will define for only small temperatures. And say suppose I have taken, one second, if I take, yeah, so suppose if this is the whole box and we have the different small molecules, and in the thermodynamics we are not considering the how the molecule is, say suppose this particular one second, if I can erase it. Okay, I think I can't erase it. Okay, fine. So if you take okay, I will write here. If I take this molecule, it will have the what do you call the attraction force towards the what do you call the binding force with this wall, and then the surrounding molecules will have the attraction and repulsion force with this molecule. So we are not including all these things. So basically what we are including was, we are considering that okay, each molecule has a ball like a sphere which is moving just. So if we are considering this, so PV equal to RT will only works if I, sorry for the handwriting, yeah. Say suppose if you have the infinite volume where we have the gas molecules, there will be no attraction between this molecule and this molecule. So that in that case, say suppose if I take that if I have 1 lakh, if I have 1 lakh rupees, and if I lose 1 rupee, still I have 1 lakh. So in the same way, in ideal gases that is the case. It says that we have the large volume and where the molecules are fitted at the random position. Say suppose if you take this one and this one, if you erase the volume occupied by these volumes, will be very far less than the changes in the volume. So that's why we'll use the PV equal to RT. Once you come to the real gases will be in the finite volume, where it will have the two molecules will have the collisions, sorry, attractions or repulsion, and each molecule will have the collisional force with the wall. So to consider these two parts, what they have done was, initially they have done, okay, they have taken the V bar, which is the molar volume, and then they subtracted the B. B is nothing but the volume which is operated by the single molecules. Okay, so it gives the volume which is the free volume, where we need to consider the so this is a free volume which we are, sorry, this is the free volume which we are considering. So that comes the V minus B. So once for the pressure, so pressure is nothing but whatever we are taking was the pressure acting on the system. So what it does was, so suppose if there is a molecule, and if the molecule goes from, say suppose it has say suppose if you have you have taken two molecules, one molecule is going and touching with it, it has some energy releasing, and it also has some pressure exerted on the molecule. And there are two molecules, if you have taken the van der Waal energy and electrostatic energy, which is for the very small molecules, these two molecules will come together at to a certain extent. Say suppose, so if this is the R, and say suppose this is one molecule and this is another molecule, if I move like this, so there will be like zero. See, this is the what you call energy force, how much energy it is required. So initially it will be near to zero, because the two molecules are very far to each other. So once the molecule comes nearer, like not attached, when it comes to the nearer, there will be a maximum energy required to pull the two molecules opposite. So but once these two molecules come together, this will go to the repulsive force. This is also exerted some pressure on the system. So that pressure we are dividing. So we are dividing the space. Suppose, so how to so you need to consider only this part. Okay, you don't need to consider this part. Okay, if I draw the better way, you don't need to consider this one, we need to consider only this part. So to consider this part, we need to consider 1 by v square. 1 by v square is nothing but the minimum volume required by the single molecule to have its either repulsion or attraction force with another molecule. Okay, that's what P by that's what we are adding. So with the pressure which we have, we are adding that part to understand how much pressure exerted on the system. And V bar, so basically what we are taking was, we are taking the volume of the system, so we are deleting whatever the space occupied by a single molecule is equal to RT. So this is how the real gas van der Waal equation was derived. So if I think, am I clear? Have you understand the top concept?
Yes, sir. Understood.
Okay, fine. Thank you. Then. So yeah, so once we have discussed the zeroth law, so basically zeroth law goes for the temperature. So once you have the temperature, what will happen to the temperature was, so we have discussed the temperature, how can the difference in the temperature can be measured, and if I say that we have the Celsius scale, Kelvin scale, and how we have differentiate the triple point and all the things. So then comes to the internal energy. So if I'm talking about the internal energy, consider a system. Say I'm considering just water molecule. I'm just drawing it. So just assume it is two hydrogens and one oxygen. Say when I'm talking about the microscopic properties, we are considering this as a single molecule or maybe three molecules, and we are considering, okay, will there be any if it is an ideal gas, we are not even considering the repulsion force or attraction forces. If it is in the real gas system, it means in the finite volume we are even considering that things. See, suppose each molecule will move around its axis, that is one is there. It will have its vibration, like if you see any molecule will vibrate on its own axis, it will have the rotational energy. Say suppose this molecule will next minute will go to here, so it is changing its position, and it is changing it's nothing but the coordinates. It is xyz, sorry, it is having the vibrational energy, rotational energy, and translational energy. So that all comes under the parts of internal energy. We are not considering that, so we are not able to calculate that in the initial days. So that's why they call it as a unorganized form of energy. So basically what is the unorganized form of energy means, so whatever the energy which is happening here inside, we need to convert that into organized form of energy. So the best example, how to say it was, we are converting the one form of energy to another form of energy, right? So basically it is same thing. If you are converting like a motor to fan, electrical to mechanical, here also we are doing the same thing. How can we convert this disorganized form of energy, like each molecule consists of certain energy, right? How to convert this disorganized form of energy to an organized form of energy? That's what the basic thermodynamics do. And in that the first law says that, we will go to the first law, and I will explain you this in further slides with the derivation and all. So these are the some basic assignment questions which we sorry, not assignment questions. So I have explained, I think, 3 questions which will be helpful for your assignment. And if you have taken the this what you call PPT or the sir's notes in the class, you can understand, you can solve, I think, all of the questions. If you have any doubts regarding the week 1, we will discuss. Otherwise I will go on to the week 2. First we'll have some for maybe 1 hour session on what is happened, and then at last I will show you some examples of how to do those questions. Further we can have Q&A. So if you have any doubts regarding the week 1, we can have it. Otherwise I will go to the work 2. Okay. So basically what I want to say was first law. So before going to the first law, I will discuss the work. Say suppose you have the two systems, where one system initially it is in at the V1, which is with the P external. So here I am not considering the say suppose here we have some balls. Balls means molecules, don't consider it as a. So as we discussed before, there is a pressure exerted by these molecules also. We are not considering that pressure. We are considering only the external pressure which we are applying through the piston. Say suppose if I am pushing it, that pressure only we are applying. So there is P external which is P1, and there is a volume V1. So say suppose this is at this position, and then what I have done was I have applied some pressure on top so that it will come down. How much it come down was, it came down the length of L, and now the new volume are V2, and the pressure which is applied on now it is P2. So if you come, so as we all know that, how can you define the work was the force acting on the body up to certain length, that is called as the work, which is nothing but W equal to force into L. So basically what is force? Force is pressure exerted by the area of the volume. So pressure equal to force by area, so force equal to pressure into area. So that's why W equal to pressure external into area into L. And you all know that what is the difference, area into length is nothing but the volume. So this is the work done, and these are the different cases. So suppose this is the first case. If you need to see, the V1 is always greater than V2, and the P1 is always less than P2. Say suppose work done by the sorry work done to the system. What I mean to say with the work done to the system was, as external you are applying some work on the to the system. So that's what. So work done to the system means you are converting from V1 to V2. So you are applying some pressure, that is called as, you are applying some pressure. Okay. Work done by the system. Work done by the system, what does it say was, it is going from down to by up. Okay. If you understand this, work done by the system means from itself it is going from down to up. Work done to the system means you are applying some work. Okay, if you apply some work, the final volume will be V2, the initial volume will be V1. So as we all know that V1 is higher, V2 is lower. So suppose it is 10 liter, now it is 2 liter. So you have done some work onto the system, it means you are applying some pressure. So that's what, then delta V will be V2 minus V1. V2 minus V1 will be 2 minus 10, it is minus 8. So it will be, yeah, 2 minus 10, it will be minus. So we already discussed that delta W equal to minus P delta V. So now why minus means work done to the system. Okay, that is a notation which every book is following. So that's why it will be work done to the system, it will be negative, work done by the system will be positive. So it will be negative, negative of negative will be positive. Now it will be next the same thing for the work done by the system. So once you have this thing, so have the one basic knowledge about how the work is working. So yeah, as we mentioned it here, why I mentioned the slash on differential equation was it is a path oriented. So suppose there are two different ways where we can apply the external pressure. One is, okay, I am applying directly such that within 1 second I am reaching from here to here, I am reaching in one step. Say suppose says that I am applying some pressure and I am directly attaining to V2. Otherwise what I can do was I go from here to here to here to here to here and then I reach here. And the first thing is directly I came from here to here, this is first path and this is the second path. Or otherwise I can say that, okay, I will give you the example, it will come. Or the second way is, say suppose if you see this one, yeah, if you see this one, V1 is greater than V2 and P1 is less than P2. If you see that there are different ways of different paths we can take it from going from one position to another position. Suppose from here to this position I can take either this route or this route, or maybe I can take like this one also. So there are different path on how the work can be done. So that's why so this P external is depend upon the, so P external means what is the pressure you are applying on the system. So it is depend upon the how which path you are moving. See suppose if you are moving this path, the dw will be one way, and if you move in this path, the dw will change. So that's why we are applying the slash on the differential. If you see any slash on, see the basically the slash and the differentiation says that it is a path it is a path oriented. So it's not that value which can get it from, say suppose from one to another. Okay, that can also be done, but that is one pathway. So this is one pathway, this is second pathway, this is third pathway, this is fourth pathway. So it all depends upon the what is the path it has taken to reach from point 1 to point 2. So yeah, if I erase it, yeah. So we have total W equal to W1 minus W2. So W1 is this one, say W2 will be this one, I'm just saying it. So if I take the W1 path, it will be like minus, say if you see, I think you can make note of it. So it is what, from where we are going, from here to, so basically W, how we can get it. So if I am writing here, so from the next class I will use the pencil one, for bear with me for today's class. So minus P, it will be like going from, yeah, so it will be dV. So you can understand that what I'm saying was, it will, there are two things. So one is path etc. So this will be 1 and this will be 2. As there is a V2 minus V1, this will be there. Once you do this one minus dP, it will be 0. So we will have only the P1 which is constant in this way, and V1 minus V2, because it is V2 minus V1. So we use the negative sign to convert from V1 minus V2. So if you take this pathway, this value will be 0 because there is no change in the pressure. It is a constant value. If it is constant volume, it will be 0. You can see this. As the volume will be constant, it will become 0. And you have taken only this one. Sorry, yeah. And you have taken for only this one. This will be like minus P external V2 minus V1, which will be like V1 minus V2, because we are going from V2 to V1. So this is initial, this is final. So I think you understand the notation why we have get this one. So here it is minus P external, dV is nothing but V2 minus V1. So that's why it comes V1 minus V2, because we have used the minus sign here. Minus of, we have taken P2 of it is V2 minus V1. Due to the minus sign of here, you got V1 minus V2. I think it's clear. Then we have P1 minus P2 gives rise to 1 minus 2. Here you can see that, yeah, if you see this condition, P1 is less than P2, so this will become a negative value, less than 0, and this will be greater than 0, which says that W2 is less than 0. What you can understand from this was, if you have taken any closed path or reversible path, if you take a closed path, which means reversible path, in any reversible path, the work done by the system will always, the work done to the system will always be not equal to 0. So that's what which we need to understand from this thing. I think the work concept is clear. Do you want me to explain again? So once, yeah, the work, once we are done with the work concept, we will go to the heat. So basically, what does the heat says? Heat has the same properties of work, which says that okay, V1 will be greater than V2, P1 will be less than P2. So it has the same properties of. So basically, what does heat says was, when the system goes from one system to another, it goes from the temperature T1 to T2. Sorry. So what we'll say in the heat was, which says that which flows into the system to change the system from the temperature from T1 to T2. So we have that specific heat capacity and all the things. So what I say was, I will give you the example. Yeah, if you take these two examples, we have taken one isolated system and one normal system. So in isolated system, you know that there will be no energy or mass transfer between the outer system and inner system. So the energy and mass will be the same, and we are applying some we are using candle to raise the temperature of the isolated system. So here the volume will be constant, so that's why it is called as the work done is dq equal to cv dt. So we are applying some pressure, we are changing some temperature under the constant volume, so that's why the heat applied here was dq equal to cv dt. And in this case, so suppose this is like a closed system where it can change the energy between this. So what is happening was, so here we have fluid. So once we started heating, what will happen was, there will be some external pressure, internal pressure which will act on it, and it will move forward. So but we are not doing any work on it here. If you see that the pressure external is constant, we are not doing any pressure here, we are not changing any pressure. What we are doing was, we are heating such that it is moving up and down. We are not adding any external pressure to move up and down. We are heating it such that it is going up and down. So that's why it is called as dq equals cp dt. You need to understand that where it will be cv dt. And if I say about, okay, we have the constant volume process in the sense that, okay, there is no change in the volume, and there is it means it can be an isolated system. If I say it is a cp dt, it says that okay, we are not changing any pressure, it is just changing with the heat, the volume of it is changing. So that's why we are doing dq equal to cp dt. So yeah, we have the work and heat, and to put the internal energy. So what we have done was, we are applying some systems and surroundings. So basically u equal to q plus w. If I say u total equal to u system plus u surrounding, so if you remember the first class, what we can say was, there will be a boundary layer between system and surrounding. Whatever going from this side to that side will be, say suppose, yeah, to put it in the good words, u total equal to q plus w. For system it will be like q plus w, then surroundings it will be in the opposite side, it will be minus q minus dw. So that's why u total equal to 0. So you need to remember one thing, in the thermodynamics the total energy will be 0 but not the work. Okay, you need to remember this thing. So the total energy of the universe will be 0, okay, but not the work. So these are the two things which you need to remember. So once we got to know the what is heat and what is internal energy, yeah. So yeah, so we will come to the thermodynamic potential. Why we need to use the thermodynamic potential was, uh, say suppose I have the system, basically thermodynamic potential or equation of state. If you hear this type of words, what does it says was, okay, I have one system, I want to predict the properties based upon intensive variables or extensive variables. We'll come to that later part. So what I need to do was, say suppose I have a system, uh, and I have some external pressure acting on it, and I want to know the properties of this system. Okay, I want to know properties of this system using temperature and volume. So I want to know the, okay, what is the properties of this system with regarding to the temperature and volume. So this is called the equation of state. So what I can write was, if you see it here, P of if you see any book or any paper or any lecture, if you see P of T comma V, it says that P is a function. So we are deriving the pressure of the system with respect to the temperature and volume. So then you are applying the chain rule. We get the du equal to dp dt by dt under constant volume, and then dv by dt equal to at constant pressure. So if you take for the ideal gas, we have PV equal to nRT. If I apply the same thing, say suppose I want to know the change in the pressure with respect to the temperature and volume. So dp equal to if I am taking the same here, these two here, and then if you have this, and I think you can understand the differentiation which is happening here. So basically you need to understand that another second thing was sometimes I might have mistaken someone. So what is the difference between differentiation and partial differentiation was, differentiation is without any constant. If you are adding any constant, once you are adding any constant, suppose you are differentiating pressure with respect to the temperature at constant volume, which is called as partial derivative. If you are just differentiating any value with respect to any value, it is called as differentiation. So this is another thing. So yeah, so I applied nRT by V underscore dt at constant volume. So the volume is constant, so this will act as a normal constant value. So nr by V is constant here. So we will get dt by dt, which is nothing but cancelled, and we have nr by V dt minus. So here we have, so here it has like constant t. So nRT, these values will become what you call the constant, and we have what we will have was dv by dv to the power of 1 to the power v. So it is nothing but a minus 1 by v square. So that's what we got it here. So this is the relation. If you have this relation, you know that okay, the temperature is raised from, say suppose if I say the temperature is gone from 1 point x to y. During this x to y, the volume has converted from a to b. Okay, say suppose I said that okay, the given system has if you see any thermodynamics question, it will be basically like this. The system has converted from the temperature 300 to 400 Kelvin. Under these conditions, the volume has been reduced or the volume has been increased. Okay, if the volume has been reduced, means what you are doing was you are cooling the system. You can see this equation, PV equal to nRT. You need to understand that suppose if I say that okay, volume has been decreased, what does it say? Well, if volume is decreased, the temperature will also be decreased. It is you are cooling the system. If you want to increase the temperature, if you want to increase the volume, what you need to do? It's a what do you call this? Directly proportional. So you need to increase it. So if I say this is increasing, it will also increase, and you need to take the if you can see the partial differentiation, so dt. So it is dt because we are not. So this is mistake. This will be a dt, basic dt, because we are not differentiating with any constant, so it will be dt. Just make sure it is dt, not differentiate. I think in the next slides also it will be the same. Sorry for this thing. Yeah, and dp equal to this thing. So nr by v will be constant at this particular value, and then you will have dt minus nRT by v square and dt. Okay, if they ask you to find out what is the differential pressure at a certain point. So this is the basic equation, and why we are doing this thermodynamic using the differential was, we need to understand that okay, if I given any property to find out using two any different states, this is the function thing you need to use. So yeah, this is one basic example which you need to for closed system. Say closed system means the mass has not been converted, the energy is only transferred. So that's why it is du equal to dq plus dw. From work we know that du equal to dq minus dw. And we know that the second law of thermodynamics says that, as we discussed in the last class also, what does the second law of thermodynamics says that so basically the first law of thermodynamics deals with the internal energy, the second law of thermodynamics deals with the entropy. So how can we convert the heat to entropy was, basically the entropy is nothing but the amount of heat done by the system to move from point 1 to 2. So basically what this is was moment of I can say it in the good terms, moment of disorderness. Just remember that ds equal to dq by t. So which says that okay, entropy is nothing but when you say, suppose if I say that uh, I I break one object from by pushing it from the top to down, so you can't reverse the object, right? So that is called as entropy. So what is the time amount of heat generated from that statement to this statement is nothing but the entropy. So we can convert the heat into the entropy. So we got du equal to tds minus pdv, and yeah, so now we can get this equation. So up to here it's fine, I think. So to get it here, what we will do was initially we have done at constant volume, if I apply, say suppose du, differentiate with ds, so this will become t, this will get cancelled out, but this is the constant value as the constant volume, so this will become 0. So then we'll have du by ds at constant volume is t. If you do the reverse thing, same thing, du by dv at constant volume is minus p. So from here what you got is, so from here we started, sorry, so basically we started with u is a function of q comma w. Now we come into u is a function of s comma v. So basically what it teaches was, we need to convert from the one form to another form by given the, suppose if the given question says that okay, we have what do you call it, we have the heat generated or work done by system, calculate the internal energy, then you can take this function. If they say that okay, we have the entropy and the volume change, then you can use this function. Okay, so for if you are talking about the open system, so what does the open system do was, suppose if you take the boiling of water, so what does the boiling of water do was, say suppose if this is the boiling of water, there will be a flow of molecule from one side to another side. So that is one, another term which will be added, that is called as chemical potential. So it will be like, so now there are three, so now if I take this one, the second function, this is nothing but now it is now we are defining this property using three different entities, variables. One is entropy, volume, and number of molecules. Number of molecule in the sense different substances. So here what we did was, initially we have different partially derived with s at constant volume and pressure, and you can see this is the chemical potential which we are adding for the open system. So mostly we will study with for the closed systems only overall the codes. If it's not mentioned any open system, it will be the closed system. And another thing was, we are assuming that all the systems are reversible, such that the work done will not be zero if it is not mentioned. So yeah, one second, I think I can't see the screen. So now comes the enthalpy. I think enthalpy, Helmholtz, Gibbs. Yes. So basically how this was defined was, there is a mathematical concept known as, I will share you the link after the class, legendary transform. If you Google the legendary transform, LEGNDRE, legendary transform. So what does they say was, say suppose these are the extensive variables. H will change with the system, A will change, Gibbs energy will change. So when this will be helpful? So when this will be helpful was, say suppose we have a system with subsystems. So say suppose this is one isolated system. If I am not drawing well, spare me. So this is, sorry, yeah. So this is the isolated system. So what we will do was, so there is one system with say suppose s comma v comma n. There is another system which says s2, v2 and n2. And if you want to understand the thermodynamic properties of this particular, see, the temperature which we are applying from the outside or the external pressure which we will apply on this inside will not particularly talk about the subsystems of the system. Okay, if you are taking whole as a single system, then the entities of pressure and temperature will act alone. But once you are considering okay, there are different subsystems in the particular system, then we need to generate the new new extensive variables with the new properties. So basically what we are trying to do was, we are trying to develop a new thermodynamic systems equation of state. So if you see for ideal gas, we are done with V equal to pressure, volume as a function of pressure and time. Here as we go further, we will have different subsystems in a single system, and for that we try to develop these equations. Along with this equation development, we can use it for the normal system also. So what I want to say was, if I talk about the legendary transform, what does it says was, okay, I will share you the link of the legendary transform where we can understand that how the enthalpy is formed. So basically enthalpy is nothing but, if you see, the enthalpy formula is U equal to, so this is the formula. If you take, what I am doing was UTD. So if I take this one, Okay, so this is nothing but differentiative of f of x equal to a into, just assume it as f of x. Okay, it's better to take, I think, next class. D of x equal to a into dx plus b into dy. Assume it as a into dx plus b into dy. So what does the Legendre transform says was, if it is the form of in the conjugate pair, so then we can write it as f minus ax or f minus by or f minus ax minus by. Okay, I think you understand. So if you take this one, it is nothing but the this minus this. If you take a Helmholtz energy, it is nothing but this minus this. If you take Gibbs energy, it is like entirely. So H is nothing but u plus PV minus delta S. If you take this one, it is nothing but f of minus ax minus b square. Using the Legendre transform, they converted the one equation into different subsystem of equations, and they are given their respective names. So this is the basically how the enthalpy, Helmholtz energy or Gibbs energy initially defined. So basically in thermodynamics, if you see, there is no proof for why it is in thermodynamics there is saying that there won't be any proofs, but it says that there won't be any logicless answer questions. Say suppose I given this enthalpy equal to u plus PV. You can apply this to any system and you can see the answer is working out. The theorem is perfectly in match with the results. So that's what in thermodynamics they given the systems, and then they let out they figured out, okay, this theorem is not is applicable. Okay, once you know what is the basic, how to write the chain rule, and then how to write the open system, and how to write the enthalpy, Helmholtz and Gibbs energy. So now we will go to the, one second, yeah, fine. So now we will take this initial one, and then we will go to the subsequent ones. So I think you can understand this. We have H equal to u plus PV. H is nothing but if I differentiate it with normal differentiation, it will be dH equal to du plus PdV plus VdP, as you can consider these two as variables. Now we know du equal to, from the initial equations, du equal to TdS minus PdV, and it is already there, and these two cancel out. So we got dH as TdS plus VdP. So what does it says was, now enthalpy is a function of S comma P. Say suppose if I given the entropy and the pressure, I can find out the enthalpy. You can understand from this equation. If there is any two forms I given, so extensive state says that, okay, I can find any different parameters of the state. And if you take the Helmholtz free energy, you will get A as a function of V and T. So if I apply this one, du equal to dv into dt, you should not apply like this. So you need to understand the whole equation, so how it was formed. If I given that, say suppose, okay, if I given that there is a volume change and the temperature change, if they ask you to find the Helmholtz free energy, you need to use, okay, you need to understand that, okay, there is a formula which says that A is the function of u comma t, v comma t, and then you need to use this. For the Gibbs energy, the same thing. It is a function of g is a function of p comma t. Okay, so once you have this formulas, now I will take this one. Sorry, yeah, just focus on. So I'm erasing this this one. Oh, yeah. So now just focus on this one. We'll go through the same thing as next one. So now I have these properties. If you remember how we done for du equal to TdS minus PdV, we differentiate initially with entropy with constant volume, we got T. If we differentiate same thing again with the volume and keep the entropy constant, we will get the minus P. The same thing we have done for different cases. If you see du by ds is nothing but T. I can do this thing also. Say suppose now these two are same. If you see, I will put it, I think it's better to use another pencil. These two are same. I can use this along with this and this two, and if it looks good, yeah. So generally in thermodynamics, what we are doing was we are making the key relationships. So that's why if you see, if there is a dH by ds at constant pressure is nothing but the internal energy with at constant volume. So these are the matching equations which you can do, and this will give the Maxwell relationship. So yeah, before going to the Maxwell relationship, I just want to talk another mathematical implementation which we have talked in the class also, as sir discussed. If I have one equation, as I said it, if you have one equation says that df equal to a dx plus p dy, a and b acts as a constants, x and y acts as a variables, you will get a with respect to, if you do as showed initial, dy by dx with at constant y gives this one, and if you do this one again with dy, it will be like second differential of y of function of f with respect to x. I think this is not need to explain it. Why I have shown this one was, if you carefully see here, okay, I have this equation, and then I converted this equation to this. Okay, so that's what Maxwell relation to do was. What the Maxwell relation do was, it will take this form. Say suppose dh equal to, say suppose they have taken this equation, df equal to, assume this equation, df equal to a into dx plus b into dy. Okay, and if you take this equation, you can write it out in the notes and try it out. If you take dh equal to t ds plus v dp and all the equation, and try to figure out what are the equations you are getting. So I am very sure, say suppose if I do it here, what I will get it here was dt by dv at constant s. If you see, if you do this thing, the same thing for here, so just take this one, and if you do it, you can try it out in the notes. If you take du equal to t ds minus p dv as a function of df equal to a dx plus b dy, this function, so now it has, we have, sorry if I am not wrong, du equal to t ds minus p dv. So now if you do du by ds, u by s, I'm just writing it as a shortcut, will gives you t, and then if I do this t dvt by dv at constant s, you can see that from where I'm going to here, this is coming from here. So same way we can match the two things. So this thing can be matched with this. Okay, so and you need to do this thing, this example. So I have given the name. So from enthalpy we will get this one. If you use the enthalpy we will get this one. So here I said that if you can see, one more thing I need to explain here was, yeah, this and this are same, the entity. So then these two will be same, because it will be at constant x, because initially it is at constant x. So then these two entity will be same thing from the enthalpy. So we will get enthalpy this one. If you do this, then you will get in from internal energy the same thing, and from Helmholtz energy you will get this equation, and this is from the Gibbs energy. So this is nothing but what the Maxwell relation says. Yeah. So once we have the Maxwell relationship, what we can do was, we will go to the properties of fluids. Why we need to do the properties of fluids? Just a second. Yeah. Say suppose that we have the state with pure homogeneous fluids, or say that I have the water. Just given the example of water, just say water, water molecule. It can be either in a liquid form, or in liquid plus vapor form, or it can be in a three-phase form, like a triple point. So now there are three phases. So now I want to calculate the properties of liquid system, I want to calculate the properties of liquid plus vapor system, and I want to calculate the properties of this system. So basically you need to think that, okay, what are the parameters I can take, how many parameters do I need to take to say suppose if I have the system of L, okay, I need to take the liquid system, and I want to calculate the how the thermodynamic state is displayed. Or if I want to take the liquid and vapor, it's like I have two-phase system, and how can I do it? If I say I have three-phase system, like a triple point, how many intensive parameters do I need to take? Okay, so that can be given by the phase rule. So suppose if I say the example of uh, system of steam and liquid water in equilibrium. So basically the degree of freedom, which gives the formula F equal to 2 minus n 5 plus n. No need to worry about what is sorry what this equation does. So what you can do is you can take this force degree of freedom equation. Degree of freedom is nothing but how many intensive variables you can play with. Say suppose to give a best example, I have taken the triple point. Okay, triple point means we have only one water molecule, but we have three different phases of the water. So now the F equal to F will be 2 minus the phases. You can see pi is number of phases. The phases here is 3, so it will be 3, and the how many number of chemical species 1, so it will be 0. It means it is only valid at exactly one point. It means you can't take any intensive variables to figure out that point. So it means it is a constant value. Okay, that is existed only that temperature and that thing. So if you see the Kelvin scale initially what we have discussed, it exists at only that point. If you change even a small bit of temperature or pressure, you can't even play with it. So that's what the degree of the intensive variable which can how many you can play with it was 0. Say suppose I'll take the liquid plus volume as here it is. So it is vapor, I have the liquid. Forget about these values. Just for 2 minutes forget about these values. I will apply the same equation here. It will be 2 minus how many phases we have? The total number of phases we have is 2. How many number of chemical species we have? 1. Okay, it means we can play with one variable. It means either you can move this one or you can either move this one to understand that okay how the steam and liquid water can vary. Okay, if I take the only liquid, see suppose there is only one liquid, it means what I have 2 minus number of phases 1, and then I have number of liquids 1, so the output will be 2. Now you can define the system either by changing the temperature or pressure. So here you can't change the one. So here you can change only one. Either you need to keep this one as constant and then you need to play with this, or you need to can change this one along with this. Okay, so you need to understand that why we are using the degrees of freedom. Degrees of freedom is basically to understand that okay how many intensive variables I can take to play with the system to understand the system properties. So this is a small example. I think it will be easy for you to understand. So can somebody tell me the answer for this one? I think there is a small question here. If you want to understand, I will explain it again. How many phase rule variables must be specified to see? We understand what is thermodynamic state, why we are using it, and phase rule variables. How many variables we need? So suppose temperature and pressure or volume, water, that will be a different kind. How many variables at least you need to understand the thermodynamic state of system? Can anybody give me example for one liquid water in equilibrium with its vapor? Am I audible? I think can somebody say hi? Can you answer like if it is possible? Can you hear me? Hello?
Yes, sir.
Yeah. So if you understand, can you just because it will be very important to understand that okay if you are taking any phase rule, you need to understand before doing the system that okay how can you apply phase rule and how many variables you may need. So if I talk about the liquid water in equilibrium with its vapor,
One variable.
one second, what I'm doing, sorry, yeah. So one variable, so basically it will be 2 minus that there are two phases and the 1. Okay, it is 1. So can you give me for the second one? Liquid water in equilibrium with sorry, can't do this. Yeah, the second one, liquid water in equilibrium with a mixture of water vapor and nitrogen.
Two variables.
So we'll see how the 2 is coming. 2 minus, so we have the two different phases, one is water vapor and nitrogen, so it will be like 2 plus So we have two different systems, so it will be 2. So it will be 2. So can you give me for the third point? The for third one, it will be like there is a three-phase system. He already mentioned it has three phase. So it will be 2 minus 3 plus, we have two systems. If you see, there is a salt and there is a solution. So there is one aqueous solution and there is excess salt. So there are two different entities. So it will be 2, it will be 1. So the phase will be 1. So this is not related to your what do you call assignment, but it will be helpful for you to understand. Okay, if anybody asks me to understand that how many phase variables are needed, so it will be easy. So yeah, so now.
Sir, but in third question, both the chemical species are salt, right? So how it can be 2 for n value?
Oh yeah, so okay, a three-phase system, it will be like 2 minus, we have three systems, saturated aqueous salt, yeah, it will be 1, sorry. If you are talking about, if I didn't mention that which salt it is, so if it is the same salt, it will be 0, sorry, it will be 1. If it is different salts, then it will be 2. Okay.
Yes, sir.
So now we have that say suppose we can't every time we can't understand that. Okay, if I say so now we understand the phase rule, and there are some important constant values which you need to remember. If you have v equal to v of function of t comma p, so the expansivity of the fluid is, what does it says was how much the volume has been increased, at constant with respect to temperature at constant pressure, gives rise the expansivity of the fluids, and the compressibility of the fluids will be given by, one second, yeah, and the compressibility of the fluid will be given by minus 1 by v. So what does it says was, until now if you see there is a, if you see the triple point diagram, it deals with the pressure and temperature, and you have another diagram which is the PV diagram, and there is another diagram in thermodynamics which is PVT diagram. So say suppose this all are like, suppose we have taken the three different variables and you have done that. Okay, if I take the PVT, it will give the triple point. If you see like a solid, liquid and the vapor, and if I take PV also, it deals with the same thing, more or less in the same way it will give. So but say suppose you have only one single phase, say suppose all the systems are in the liquid phase, and to understand the expansivity and the compressibility of the fluid, so these are the two empirical formulas which will be derived, and you need to remember these two. Expansivity means how the fluid is expanded with respect to the changes in the temperature, and the compressibility will, one second, yeah, and the compressibility will deal with the how much the volume of the system is decreased under the constant temperature for the single phase region. This is all for the single phase. Okay, so once now up to now we have discussed that. Okay, we have different equations. I'll share you the appendix file which how legendary transform, using the legendary transform we converted the internal energy to enthalpy, Helmholtz and Gibbs energy. Why we have done was, so we can see the, basically if you take one system, as we discussed that we have taken one system, the temperature and pressure will be the volume. These three will be the most suitable things to describe the equation thermodynamic state of the system. This system can be explained, but if we have like n different systems, say suppose inside the systems you have two different systems where the internal energy will may increase from here to here or may decrease from here to here. At that time, to define the each subsystems of the system, we need to understand the more properties of it, how much of the heat is transferred from this system to this system or from here to here. So that time what they have done was they have rearranged the internal energy formula to enthalpy, Helmholtz and Gibbs energy. So another thing was phase rule, to understand that okay, how many systems is how many phase rule variables. Variables in the sense, okay, if I take if you take this example, which is 2 minus 2 plus 1, which is one variable. Either you can keep 1 as a constant and you can play with 1, and you can understand the properties of how the system is changing. But for triple point you can't change anyone because it is coming at the particular location. So as of now we have discussed this thing. uh, yeah, I think if you have any questions regarding the concept, I will explain it again. So yeah, whatever we have discussed, it is for the closed system. If you have the open system, we need to add the differential term which we are adding here. I think, one second, I will show it here. Yeah, if it is open system, what we'll have, we have the number of molecules which we have in the same. If it is single, if it is like open system, there will be a transfer of molecules from outer system to inner system. So that part we need to add. It will further will go to the chemical potential, because chemical potential is nothing but a sigma of this value, because we have, it will be sigma of this Sn comma V from I to N. So this is nothing but the chemical potential change in the number of molecules. So if you are talking about any open system, you need to add this chemical potential term to all the systems. Say suppose for enthalpy, yeah, for enthalpy you need to add it here. For Gibbs you need to add it here. At the end also it will come. So whatever we are talking about systems are closed systems. So it says that eventually we are talking about the open systems also. So as the open systems will not have much effect, so basically here it will be like how to say it, dg by, it will be dn at the constant time and pressure. You can see this one, this two will go here. The same thing here, here it will be constant volume and temperature, here it will be constant entropy and pressure. So if you are understanding for the closed system, then you need to add the chemical potential term to the end to add for, to applicable for the open system. And this formulas you will get it from the I think this is also in the slides, which gives you a double derivative. Say suppose initially we have the equation, you need to get this one, you need to derive it, and once this you have, that is 2, you will get this from the internal energy, enthalpy, Helmholtz and Gibbs. So then we have the phase rule. So basically if you see the story which we are prolonging is nothing but how the temperature, once you have the temperature, how the work is done regarding that to temperature. Say suppose we are not changing, we are not yet to go to the fancy terms. As of now what we have discussed was, we have the temperature initially, okay, somebody has derived the temperature, okay, we have taken that temperature, okay, we understood that how the temperature rises will work, and then we have taken one system, we are applying temperature changes, and we are checking what will be the changes in that thermodynamic system, okay, attaining the equilibrium, after attaining the equilibrium. So these are the basically we are understanding. Then we add the entropy term to the same thing. Entropy term is nothing but the moment of disorderness or randomness, disorderness or randomness. So what is saying that how to, in the forward time, what is the changes occurring to the system. So and whatever the say they are the hero heroines, and these all are the characters which are helpful to move the, to push the molecule from this end to that end. Okay, so basically what we are doing was, if given, say suppose if I have seen the engine, uh, if you take if I have the, one second, I will show you one for the example. I think here only it will come, sorry, not here. Yeah, so this is the basically nothing but the engine, how the turbine works. So initially you will have the volume, big volume, you cool it, and then you heat it, then you again heat it, then again you cool it. So basically it works on this principle. So what you are doing was, you are converting one form of energy to another form of energy. So basically thermodynamics does this. So yeah, so as of now we discussed the topics related to, so we are discussed that why we are taking the enthalpy or Helmholtz or Gibbs energy, because no one knows why that how to derive this form. Yeah, that derivation, if you want to sound technically, that comes from Legendre transform in the mathematics, where you can do the differentiation. If you have the differential equation, we can convert this equation into the conjugate pairs. From that the enthalpy, Helmholtz energy and the Gibbs energy is derived. So once they are derived, they have done its properties, they check the properties of the system, and they verified that okay, it is working properly. So why do we need to take these systems? Was when we have the subsystems where the temperature and pressure is not the constant overall the system. So then we need to change with this. So that's why we are adding the more extensive variables. So if you see, this is the extensive variable, this is also extensive variable, this is also extensive variable. Extensive variables, if you see our first class, what does it says was, Extensive variables are the one which will differ with the time. Sorry, if I change the system size, suppose you are increasing from say suppose if the system is like this, if we increase it like this, the internal energy changes. Once internal energy changes, enthalpy changes. Once enthalpy changes, the Gibbs energy will change. Once the Gibbs energy changes, the Helmholtz energy changes. Okay, so this is what I want to say about the extensive variables. Basically, initially we have taken the intensive variables. We started with the intensive variables, so we have taken the volume. How does the changes of volume studied through thermodynamics was done through the intensive properties. Now, if the system is big and if the system is complicated or complex, we are going from to the extensive variables. And then to understand that how each one is related, I will show you the with the example some problem which sir was discussed in the class. You can understand much better these formulas. Okay, you don't need to remember everything, so you need to remember at least if you have the time in the exam also you need to remember the internal energy, and if you remember the legendary transform and what is the things will go from enthalpy to the closed system, then you can do it. I think this all are the 1 minute time. So if you calculate this, you can calculate this. If you calculate this, you can calculate the Maxwell equation. Once you are at the Maxwell equation, I mean, if you remember this all, you can't remember at a time. So better to remember, okay, what is internal energy and how does the internal energy goes to the enthalpy. Don't need to learn the enthalpy also. If you know the legendary transform, say suppose I can write it here, legendary transform. What does it says was df equal to a dx plus b dy plus c tz. Then so this will be if you want to transform this system into so this two acts as a conjugate pairs. So now we can develop a new equation such that y minus ax is one equation. There will be another equation which says that y minus by. You are saying that I am not differentiating it, and there will be another equation. It depends, like if you have more variables it will be more f minus ax minus by, and there will be like same thing. I think you understand the concept what I'm saying. So if you remember, okay, which one gives enthalpy, which one gives Helmholtz energy, which one will give Gibbs energy, if you remember this thing, okay, then everything else you can calculate, I think. So these all things you can calculate from that. So then comes the phase rule. Okay, how many variables we need, and the expansibility and compressibility factors. So expansibility says that how much the volume has been increased at constant pressure with variation in temperature, and the compressibility gives how much the volume is reduced with constant pressure and increase. Compressibility is nothing but, if you see, this is the diagram. Sorry, not compressibility, expansivity. If I am talking about the expansivity, the pressure is constant. Okay, the external pressure is, see, the pressure which I am talking is external pressure. Here the pressure is constant, there is some volume, and you are applying heat. What it does was, it slowly increases the system. We are not adding anything, so here the work done will be 0. You need to remember that, because work done is nothing but minus pdv. If you remember, it is I am not putting the sign. Okay, I will put the sign minus pdv. Minus p is the work which you have done, pressure is nothing but the work, so you are not doing any work, so this value will be 0. So even though you have the change in the volume, the work will be 0, so the work done here will be 0. So this is the example of this case. I think this is the case. So this is like, you have the constant temperature and you are applying some pressure on it. Say suppose from the up you are applying the pressure, you are checking how much volume is decreased. Say suppose from here to, it is moved up to here, so you are checking, okay, this is at v1 and this is at v1, and what is the difference in this v1 to v2. Okay, this is the compressibility and this is the expansion. So these are the formulas which will be given, that formulas. I think I am clear. If you have any doubts regarding that, you can ask me. Okay, I think this is one of the problems solved in the class by sir. So can you tell me what we are discussing here? So what are the important, I think I given. So here in the question given above, you need to understand what are the parameters given are and what they ask us to find. So can you tell me what are the parameters they given? What you can understand from this question? Say, if you take any thermodynamics, you need to understand, you need to make the pieces of that question. So can you tell me what we have done here? What we can do? You can hear me, right? I think so. Hello.
Yes, sir.
Yeah. So if you're not understanding, you can ask me that. I will repeat the question. So can you tell me what are the things has been given here such that we can understand that how to do the calculation? So
They
basically,
have given the pressure and temperature
yeah.
and asking us to find the enthalpy and entropy.
So the pressure, they said that okay, it needs to take water. So what the question says was, a high pressure water vessel is being designed for a bioprocess plant. Okay, this is some technical point. It needs to take, so from here thermodynamics starts. It needs to take water that is available at, okay, it is available at P1 and T1. It is available at this point to P2 and T2, sorry, P2 and T2. Uh, Change in enthalpy, so they are asking to calculate the enthalpy and entropy, and they given the uh, Cp, volume. So what they given was bioprocess plant volume, and alpha. Alpha is nothing but the expansion, right? So these are the parameters they given. So output they asked was, so they asked to find out the enthalpy with respect to the time and pressure, and entropy with respect. So if you write like this, it will, the off question will be done. So once you understand that, okay, what are the given parameters, h in the terms of t comma p, yes in terms of t comma p, okay. So now, yeah, so up to here any doubts? So from this you need to write the equation like this. Once you have written the equation like this, I'll come with, just write these values in your notes if it is possible, if you want to solve it. So once you have written this value, so what we will do was, now I am writing the both equation like this. So now I am differentiating the equation with the partial derivatives, keeping dH with the dt at constant pressure, because we need to calculate with the temperature and pressure, as the functions given the values are temperature and pressure changing. So this is the basic one, okay. So once we have this, we know that Cp equal to dH by dt. So how we got this equation? So can anyone tell me? So it will be easy for to understand for you. So how we got it to this equation? So if you take, okay, I will explain it here itself. Sorry. So yeah, if you remember, initially we have discussed that dq equal to Cp dt. If you remember, initially I tell that Cp dt. Okay, keep it like this. Now enthalpy is nothing but U plus Ps. So if I do the U plus Cs, then I will do the differentiation. What I get was, what is U? U is nothing but, how to say it, Q plus W plus PV. I think I'm writing correctly. So sorry, yeah. So now Q is, now I am applying dq. Otherwise I can write directly also, right? So that is far better. One second. So why to write this one also? So basically now if I write H equal to, we know that U equal to T delta S minus P delta V. From here, if you see, yeah, if I'm taking this equation, we already know that du equal to T delta S minus P dV. So yeah, du equal to P dV. So now if I take H equal to dH equal to, so dH equal to T delta S minus P dV plus P dV plus VdP. So this term came from U, this term came from PV. I applied the chain rule as both are the variables P dV plus VdP. So if you see, this will be cancelled. Now we have delta H equal to T delta S minus VdP. Okay, so now I want to do division by delta T at constant pressure. So if I am talking about the constant pressure, this will become 0 because it is constant, so this will get the constant. So then this will get the, sorry, I'm doing for the down one, sorry. For this I'm doing dt at constant pressure. So now we have this equation, I have proved this equation, sorry, here. You need to understand, if you are taking this equation at constant pressure, dH equal to dq plus dw, right? Sorry, dH equal to dq plus dw. One second. Yeah. So now it comes as, so now dH equal to dq minus pdv plus path taken by the w. As if we are talking about the constant pressure, this will become the 0, and I think you guys are not getting the, one second, I will explain it in a good way. So for this, what we need to do was dH equal to U plus PV. U is nothing but Q minus PdV, work done with path taken, plus PV. Now if I apply the differentiation, it will be QU minus PdV plus path taken plus PdV plus VdP. So if I am talking about this and at constant pressure, so this one will get cancelled. You know, right, the path means what is the change in the path is, so basically this equation is nothing but PdV only. So it is nothing but the differentiation. When I am talking about the, what do you call, the slash in the differentiation, it says that it is directly dependent upon the path. Once I talk about that it is a constant path, then it also becomes 0. This is also get 0. So then we got dH equal to dq, sorry, dH equal to dq, which is nothing but dH equal to, at constant pressure, Cp dt, which gives rise to dH by dt equal to Cp. So this is what you got. Understand the equation, or do you need to explain me again?
So can you explain it again?
Yeah. So basically we have dh equal to, sorry, h equal to u plus v. Okay. This is the basic equation we have. Once we have this equation, I'm not writing anything. I'm not converting h. So what I am doing was, you know that u equal to q plus w. Okay. So u is nothing but q plus w. So now the w will be two. One is the basic equation of w is p dv. Okay, this is the basic one. So this is u has become q minus p dv, to put it in simple words, and we have pv. If I apply the differentiation here, it will come as dq minus p dv plus p dv. For this I am writing, which is this part. Okay, wait 1 second, I will explain it in a nice way. Now we will get clarity. H equal to, so u plus, sorry, u plus pv. Now I will focus on this part alone, sorry, u part. It will be q minus w. Minus sign denotes the work done to the system. So now it will be h equal to, so now if I apply dh, it will become as dq minus dw. Otherwise you can keep it as plus also. For now I will tell you dw. I am talking about only the internal energy. Now the dw, so if you take the dw, we'll go to the first slide. So now if you take the dw, which is the difference between the first equation and second equation, where is it? So basically if you take this equation, we are taking dw as minus p external dv. Okay, so I am taking this equation. For then it will go like dq minus p dv. Now what I am doing was, so for this I am writing here as plus p dv plus, applying the chain rule, plus v dv. So now this p dv and this p dv will be cancelled. So now for the dh, what we have is dh equal to dq plus v dp. As I am talking at, as we know that h is a function of, in our case h is a function of temperature and pressure. So what I will do was, I will differentiate this with dt at a constant pressure. Okay, if I do the constant pressure, this will get cancelled out. Okay, because it's not the constant term. I mean dp will come 0, because if I say constant, it means p1 equal to p2. If p1 equal to p2, then dp equal to 0, then the whole system will be 0. So what we have is dh by dt at constant pressure equal to dq by dt at constant pressure. So if you know this equation already from the heat, saying that this will be this, and it is equal to Cp. So that is this one which we have written here. Is it clear? I will explain again also. Hello?
Yes, sir, understood.
Yeah, thanks. So if you didn't understand, then I'll explain it again also. If you have any doubts regarding this equation, because from the next onwards, so what you need to understand here was, so once you got the dh, you need to change it to the system of what is the equation. So here it is a necessity of with the T and P. So now I converted the whole enthalpy equation into T and P. Okay, so now I got dh equal to this one. Now I have taken dh equal to this equation. Again, this equation I think you got it from here. this one, the differential equation. So this equation I have taken as h equal to u plus pv. This is also same thing, but I differentiated it again and I came to this part. And here if you see, I think this you can understand, right? This part I have done with the dh by dt at constant pressure is nothing but ds by dt. Have you understand this one, this topic, how we got from here to here? Hello?
Yes, sir.
Yeah, if you, because we will come for like, if I do dh and divide by dt with a constant pressure, once there is a constant pressure term it will get 0, so this is nothing but t dst. And if I apply this into this, we will get ds by dt equal to cp by t. So now you can understand that you have three terms. So now you understand that what, okay, if I take entropy as a function of temperature and pressure, you know what is, how it is varying, you know how enthalpy is varying with this. Okay, now we need to know, so now you figure out, okay, how this is happening and how this is happening. Now we need to figure out how this is happening, this and this. So for that we are going to the Maxwell equations. In the Maxwell equations we got this equation. If you see, okay, this equation from the, sorry, from Maxwell Gibbs energy, if you can note it down, from this Gibbs energy I have got into this equation. So this is nothing but the expansion fund. So it's nothing but I have taken temperature, I am applying some temperature, it is at the pressure, so the volume is increasing from this point to this point, it is nothing but the expansion alpha, and we got the V. Okay, so now to get the H relationship with P, so now we got the P. So now to get H of, now what we will do was, to get this we will use some other expression. So I have taken enthalpy as a function of entropy and pressure. So then I applied with the pressure, okay, constant pressure. So once it is applied constant pressure, we already know that this parameter. So from this parameter we'll come to, from, if you apply this parameter here, you will come to this equation. So can you try to do this derivation once? If you have any doubts I will explain. I think it will take less than some time. Can you try to solve these equations? Okay, if you can understand how to get h, this term and this one and this one and this one. So these are the four important terms which you need to figure out. So if you can try it out, and if you have any doubt, so it's better to it's better to try it out by yourself. So can you try it out if it's possible? If you got any doubt in any equation to get up to here, so at the end the equations will be look like this. So if you have any doubts on how to coming from this point to this point, I will explain you. It will take 2-3 minutes more on this slide. So let me know if you are trying. So have you understand this concept what I am explaining here? Think. So if you read the Maxwell equation, so this is from, I think this you understood. This is also, it's understandable, easy one. This is also easy one. This two came from Maxwell equation, Maxwell and expansion. Maxwell and expansion. You can later on also you can try how to go from. So this is from the basically I have taken the internal energy and I didn't convert it. and then I taken it this equation, the differential equation. From here I got this. Then I use the Maxwell equation and expansion equation. I got this two. Then I use the entropy as enthalpy as a function of entropy and pressure. Then I got these parameters. So you know what is the expansion and what is this thing. So basically, yeah, from enthalpy also. So this is also, I think you can get it. So you can try it later on. If you didn't get it, you can ask in the discussion form. I'll send you the clear. If you have any doubts regarding this, it is the same problem which from the NPTEL video also. I think I'm clear about. So if you take these values and if you put it in this equation, at the end you will directly see here the Cp value is given. You know the temperature difference from the one point to another point. You know the total volume. You know how much expansion is happening, and you know which temperature you are focusing on. The final temperature which you are talking about. You know the pressure change. The same thing for here also. So here you need to, what you need to do was, S will be like you need to apply the integration to get the ln of T1 minus T2 and the P. Am I clear regarding this problem? If you try the thermodynamic equations later on one by one, you will understand okay how to go from one point to another point. Okay, these all are like as initially we discussed, the question can come from in any point of view. Like they will give two parameters and ask to find out the third parameter. What you can do was initially itself you can write the Maxwell equations, all the derivations, uh, which you should not be remember, because at the midpoint of the exam you will never get this point that okay, can I do this one. So I think it will be better through practice. Okay, so any doubts regarding this problem? Hi, can you hear me? I think anybody in the call. Think yeah. I understanding the if you want to explain me, I will explain it again. If it's okay, I'll come back to this problem again. So this is the second one. So can you tell me what is happening in this question? Hi, can you hear me? If it's possible. Hello.
Yes, sir.
Yeah. Have you understand the first question? Like what is the we had discussed there? The derivations.
Yes, understood.
Yeah, thanks. Can you explain me this? Sorry. Can you Can you give me what is the input parameters and what we need to calculate from here, if it's possible? So what they said was ammonia gas is purified in purifying water supplies. That is a chemical reaction. 1 mole of pure ammonia is stored in a container in the basement of the building. The container walls can withstand a pressure differential of 20 atmosphere between the inside and outside of the container. The container was placed near the radiant heater. So what they said was they placed it near the radiant heater. In the basement, ammonia expands with rise in its temperature. So something is expanding with rise in temperature, and this will lead to the pressure buildup and explosion of the container. Calculate the change in pressure with respect to the temperature. Okay, they asked to find out this value, dP by dt. And the case they have given was, so what they said was, the container walls can withstand a pressure differential of 20 atmosphere between the inside and outer side. So suppose it can uptake the difference between the 20 atmosphere. And what they have done was they have kept it in the container, the ammonia, as a gas. If you can see, ammonia gas. So inside there is ammonia gas, and they are applying some heat, radiant heat. So that's what, right? So you can see the container was placed near the radiant heater in the basement. Ammonia expands with rise its temperature. So ammonia expands, it means there is a change in the volume. So the volume is changing, and this will lead to the pressure build upon explosion. So what they said was there is some pressure exposure is happening. So how can you calculate the change in pressure and the temperature? So if you remember the expansion formula, the volume expansion, we have the formula of 1 by V dV by dt, and if you see the compression formula, we have minus 1 by V dV by dP. So I'm not talking about the partial differentiation, the partial differentiation is at the constant pressure and at the constant temperature. I'm talking about the normal differentiation. So this is what we are getting. So if I do K by alpha, what I'll get was dP by dt. I understand the concept what I'm trying to explain here.
Sir, if we take the ratio, won't it be dt by dp?
K by alpha.
Yes.
Oh, sorry. Alpha by K.
Yes, sir.
Yeah, alpha by K. I think. Sorry, yeah, my mistake. Yeah, it's alpha by K. So basically, see here, what you need to understand from the point of view that they are given that there is a container with a radiant heater. So if you see this thing, you should understand that okay, here there is no other molecule. So basically, if there is very small molecules, see if they didn't ask the entropy and enthalpy terms, and you don't need to go to that extent. Okay, if they given any find the enthalpy entropy to the closed system, then only you need to find out okay, do I need to think about the internal energy, enthalpy, Helmholtz free energy? If they didn't talk about these things, you don't need to make the life complex. So what you can do was, okay, what are the other equations which you know? So you know dq equal to cv dt. So this is regarding the work, but they didn't ask about any work. So they ask about the pressure change. So here we are talking about the constant pressure. So where there is a pressure change option which you see, other than the extensive variables, thermodynamic states, is this 2 points. So from these 2 points, if you take the ratio, you will get the alpha by K, and the given values are in Pascal. If you convert it into the atmosphere, you will get the value. And I think you have the same type of typical question in the assignment also. So just understand that whether they ask the calculate the change in temperature with pressure or with the pressure and temperature. So if it is alpha by K, it will be d by T. If it is K by alpha, it will be opposite. I think I'm clear about this point in this example.
Yes.
So yeah. So this is the question given, the next question. So can you understand what is the question given? A system consists of 0.25 kilomole of oxygen gas. Okay, some amount of oxygen is there. They given initial temperature and pressure. If the system follows a constant volume process, so you should understand that there is a volume is constant. Okay, if the volume is constant, it means, can anyone tell me that what is volume constant? So what do you mean by volume?
Isochloric process.
Sorry?
Isochloric process.
Yeah. So then you have the change in the internal energy, the heat capacity is given. So they ask you to find out the calculate the change in the internal energy. Yeah. So they asked to find out the du, and the values they given was Cp and Cv and the T1 to Tt and the oxygen, how many moles are there. So what you can do, so again it's better to at least no need to draw the drawing in this. At least if you make a small diagram out of your page, you will understand that okay, they given the system with oxygen and the constant volume. So if it is constant volume, they given the parameters are Cv and Cv. You know that dq equal to Cv dt. As you already know that du equal to Q plus W. Here W will be 0 because constant volume, so it will be only Q. So Q will be CV delta T. Yeah, CV delta T. This is for the 1 kilomole. They given for the 0.25. You need to find out for the 0.25 kilomole. So 1 kilomole. This is the formula for 0.25 kilomole. You need to add this one. Okay. Understood? So for 1 kilomole, if it is CV dt for 0.25 kilomole, sorry, yeah, it will be 0.25 into this value. You understand the logic here?
Yes, sir.
And the second question also. So estimate the work done. So how much work it will be done during the constant volume process? So if I ask this question, for the same question, they ask to calculate the change in internal energy and the work done by the above system. So can you give me the answer? So work done will be 0. I think. Can you explain me why? I think have you got it? Why W equal to 0? Is there any doubt regarding why W equal to 0? If no, then I will move on to the next question.
No, sir.
Okay, fine, thank you. Now here it is. So they are given the next question. So 1 kg of water is vaporized at constant temperature and the constant pressure. So now it is T is constant, sorry, T is constant, P is constant. Calculate the delta H, sorry, delta H. For the system, given the specific volume of the liquid, they given the volume of the liquid, volume of the vapor. So basically it is an open system. So where for this change, they say that this is heat added to the system, so they given that heat is given. So I think we all know that dH equal to, sorry, dH equal to Q, sorry, H equal to Q basically. So we solved it, right? H equal to, from the, I think we solved this equation. So that's why if you do this value into kilojoule, you will get the answer. Any doubts in this question?
So can you explain this?
Yeah. So say suppose you have taken the system and they said that for this change, they're asking for the constant temperature and constant pressure. Okay. So what is happening was the T is constant and the pressure is constant. If you see, once again, I'm just coming to back to that equations. So now we have the equation. So delta H we need to figure out. So what they said was it is a constant temperature process. so we can't take the temperature, and it is the constant pressure. So we have the two different terms as a constants. So calculate the delta H for the system, okay, of the given system. So okay, so now it will be like, you can write delta H equal to U plus PV. Okay, so now if I take a U as Q plus W plus PV, and now it is, sorry, I think you can also try dq plus dw plus PV. Sorry, PV means same thing, dPV plus VdP. So they said what is it, constant pressure, so this will be 0. Okay, now, so now if we come to this, so now it is dq work, you can take it in the two work, you can take it in the two forms. One is, choose the answer, yeah, work is minus pdv plus dpv. So yeah, so now we have this equation, we have the is added to the system. Okay, we have the pressure, we have the change in the volume, so this will become, sorry, this is 0, right? We have only two terms, dq minus pdv, dq minus pdv. So can you try and figure out that how much answer it is giving, dq minus pdv? Dq is nothing but 1450 14. I'll also try. So you understand, right, how this formula came? Is it clear for this formula? Hello?
So, but minus PdV and plus PdV would get cancelled, right? When we derive
Yeah,
over here.
sorry, yeah, sorry, yeah. One second, I think the confusion is there. So here I forgot to write one more term. So what you're saying?
So
Yeah, so
W is equal
minus
to
TV and plus dV, this will cancel, yeah.
Yeah.
So this term is cancelled, and I'm making everybody confused. One second. So this is the basic equation, U plus PV du, U is nothing but Q plus W plus PV. So now if I apply differentiation, so it is dq, sorry, it will be minus pdv, it will be plus pdv plus vdp. So now this one, sorry, this and this get cancelled, this is cancelled because of the constant pressure. So now that's why we have dh equal to dq. So the given value is, q value is 1430.5 kilocalorie. So now you can convert into 4.184. If you multiply with the joules, you will get the answer in the joules. Now is it clear? I got confused, yeah.
Yes, I understood.
Yeah, so yeah, if you have any doubts regarding the concept, you can ask me. So basically, if you take any equation, you need to go to the basic one, which we derived from these things. The equation is, sorry, not this one. We have this equation, right? If you remember, initially we have UTDS minus PdV. I will just mention it here. So if you have this equation, the enthalpy will be U plus PV. Helmholtz will be U minus TS. The Gibbs will be entirely this one. here it will come, sorry, here it will be minus, it will be plus. So if you remember this equation, if they ask you to find out any terms, let's suppose if I ask about enthalpy, we can calculate from this to here. If you remember directly last one, okay, dH equal to dq, it will be very difficult for you to understand. So it's better to go from the, sorry, it's better to go from the basic dH equal to u plus PV. Even though if you take 2 minutes of time, it's better to derive it. Okay, u plus qv plus PV, because as of now I just made the mistake. So dq minus PdV, this is get cancelling. Okay, constant pressure, this is get cancelled, and dq is the pending, and you will get this one. So if they ask about any Helmholtz free energy or some different free energies also, you need to go from the scratch. If you are not getting any value, you need to understand from the, okay, if I use the Maxwell relations or reciprocal relations, do I get it? So basically this all called as a Maxwell relations. See, suppose, yeah, this is called as reciprocal. Say reciprocal in the sense you are doing some equations to, sorry for the clumsiness, yeah, these all are called as the reciprocal equations, where you are getting the derived terms. Okay, so if you have any doubts regarding the last week assignment, I mean, I think the week's assignment is due is not done, so I can't explain that question. So the next week I will try to explain all the questions of the week 1 and week 2. If you have any doubts, I think if you read the NPTEL classes or this video, I think it is, you can understand that concept better. So this will be uploaded in the YouTube. I think you also will you already get the links regarding this. If you have doubt, you can look into it, and if you find any mistakes or if you want any understanding, you can do it in the discussion forums. If you have any doubts, you can ask me. If there are no doubts, then thanks for attending the class. Next week we can solve the first week and second week tutorials, and then we will follow up by the next week classes, the update of from the third law, or how we can. So basically I plan to do it in this way, like zeroth law, first law and second law, how to mix it. And if you have any queries, you can ask in the discussion form, and the next week we will discuss the same. And thanks for attending the class. If you have any doubts, you can ask, otherwise we will end the session.
No doubt, sir.